You have seen cargo ships your entire life, in ports, in documentaries, in photographs of containers stacked 20 meters high crossing the ocean. You have never once looked at one and asked why it has no sails. That seems like an obvious question. Ships use sails for thousands of years. Sails cost nothing to run. The wind is free. And right now, with fuel prices at record highs and the shipping industry under enormous pressure to reduce its emissions, free propulsion from the wind sounds like exactly the kind of solution everyone should be rushing toward. Nobody is rushing. And the reason nobody is rushing has nothing to do with the technology. The technology works. It has worked since 1925. A ship crossed the Atlantic using it over 100 years ago and burned less than a third of the fuel it would have needed otherwise. The reason is something much harder to solve than engineering. It is a problem of incentives so perfectly designed to prevent progress that the solution has been sitting in plain sight for a century while almost nobody uses it. But before we get there is a question nobody asks about those rotating cylinders you sometimes see on modern ships. Because what they are doing to the air around them should be impossible. To understand why cargo ships abandon wind power in the first place, you need to understand what a cargo ship actually is. A cargo ship is not a vehicle in the conventional sense. It is a floating warehouse with an engine attached. Its entire design is optimized around one thing: moving the maximum possible amount of goods between 2 points in the minimum possible time at the minimum possible cost. Every square meter of deck space is either carrying cargo or providing access to the holds below. The hatches that allow containers and bulk goods to be loaded and unloaded have to be reachable by cranes. The deck has to be clear. The faster the loading and unloading, the more trips the ship can make, the more money it earns. A traditional sailing rig, masts, rigging, sails covering the deck, would make all of that slower. It would reduce cargo capacity. It would require a crew trained in sailing, not just in engine operation. It would add maintenance costs, and it would make every port call longer and more complicated. When steam power arrived in the 19th century, ships abandoned sails almost immediately. Not because steam was obviously superior in every condition. It wasn't. But because it was controllable. You could go where you needed to go, when you needed to go, without waiting for the wind. The economics were undeniable even before the technology was fully mature. Coal gave way to oil. Oil became cheaper and more energy dense. The modern cargo ship emerged, a vessel that burns hundreds of tons of heavy fuel oil on a transoceanic crossing, emitting sulfur, nitrogen oxides, and carbon dioxide at a scale that makes individual cars look irrelevant by comparison. And then fuel prices started rising, and the pressure to decarbonize started building. And engineers started asking the question that seems obvious: why not use the wind again? The answer is not sails in the traditional sense. Cargo ships cannot have sails. The deck access problem is real and unsolvable with conventional rigging. But there is another way to extract propulsive force from wind that has nothing to do with catching it in a fabric. It uses a physical effect that most people have seen demonstrated with a football and never thought about again. When you curve a football, when a striker bends a free kick around a wall into the top corner, the ball is not following a straight path because of the wind. It is following a curved path because it is spinning. The spin deflects the air around it unevenly. One side of the ball has air moving faster across it than the other. The difference in pressure between the two sides pushes the ball sideways. That effect has a name. It was described mathematically by the German physicist Heinrich Magnus in 1852, and it is called the Magnus effect. Anton Flettner, a German engineer, looked at the Magnus effect in the early 1920s and asked a question nobody had asked before. If a spinning object deflects air and generates a sideways force, what happens if you put a very large spinning cylinder on a ship and let the wind blow across it? The answer, which he confirmed through testing and then through an actual ocean crossing, is that it works. It works extremely well. Here is the number that makes this real. In 1926, a ship called the Baden-Baden, fitted with 2 of Flettner's rotating cylinders, sailed from Hamburg to New York via South America. The crossing covered 6,500 nautical miles. A conventional ship on the same route would have burned approximately 45 tons of fuel. The Baden-Baden burned 12, not 12% less, not 12 tons fewer, 12 tons total. A reduction of more than 70% compared to what a conventional vessel of the same size would have consumed on the same route in 1926. With technology that a single engineer developed from a physics principle that had been described 70 years earlier. The cylinders themselves are simple. They are large hollow tubes mounted vertically at the edges of the deck, clear of the hatches, not interfering with cargo operations. An electric motor spins them. When the wind blows across a spinning cylinder, the Magnus effect generates a force perpendicular to the wind direction, pushing the ship forward. The faster the cylinder spins, the stronger the force. The direction of rotation determines which way the force is applied. A control panel on the bridge adjusts speed and direction. That is the entire system. They can be hinged to lie flat when the ship needs to pass under a bridge. They require almost no maintenance compared to a conventional engine. They have no moving parts exposed to the sea. They do not interfere with cargo loading or unloading. And in the late 1920s, as the data from the Baden-Baden was being analyzed and the technology was being refined, the Great Depression hit. Demand for shipping collapsed. Fuel became cheap. The economic pressure to innovate disappeared. Flettner rotors were abandoned. They have been waiting ever since. Modern tests on ships fitted with Flettner rotors show consistent fuel savings of between 5 and 30% depending on the route, the wind conditions, and the number of rotors fitted. On routes with reliable wind, the North Atlantic, parts of the Pacific, coastal routes, and trade wind latitudes, the savings are at the higher end of that range. 5 to 30% of the fuel burned by a large cargo ship is not a small number. A container ship crossing the Pacific burns roughly 150 tons of heavy fuel oil per day. A 10% saving on a 20-day crossing is 300 tons of fuel. At current prices, that is hundreds of thousands of dollars per voyage, per ship, per crossing. The technology is proven. The economics, when you run the numbers for individual voyages, are compelling. The environmental case is overwhelming. Several shipping companies have fitted rotors to vessels and confirmed that the data from real-world operation matches the projections. And yet the global fleet of cargo ships numbers around 50,000 vessels. The number fitted with any form of wind propulsion system is fewer than 100. The gap between what the technology can do and how widely it is used is not an engineering problem. It is an economics problem. Specifically, it is one of the most perfectly constructed incentive failures in modern industry. A cargo ship is almost never owned by the company whose goods it carries. The typical arrangement in international shipping is that a ship owner builds and maintains a vessel and then charters it to a company, a charterer, that uses it to move cargo. The owner pays for the ship, its maintenance, its crew, and its capital costs. The charterer pays a daily rate for the use of the vessel and covers the fuel costs for each voyage. This creates a problem that is almost elegant in how completely it prevents progress. If a ship owner installs Flettner rotors, they pay the installation cost, typically several $millions per rotor. But the fuel savings go directly to the charterer, who pays less for fuel on each voyage. The ship owner has spent millions of dollars to save money for someone else. The owner could try to raise the charter rate to recover the investment. But the shipping market is competitive and transparent. Charterers compare rates across dozens of available vessels. A ship with a higher charter rate loses business to ships without rotors that charge less. The owner who invests in the technology ends up worse off than the owner who does not. It is the same problem as a landlord installing insulation in a rental property. The landlord pays for the installation. The tenant pays the energy bills and benefits from lower costs. The landlord has no financial incentive to insulate unless the law requires it. The only solution, in shipping as in insulation, is regulation, a rule that applies to every ship in every flag state so that no owner can gain a competitive advantage by avoiding the investment. International shipping regulation works through the United Nations International Maritime Organization. Any rule that applies globally has to be agreed by member states and implemented uniformly. The process is slow, contested, and subject to the same flag of convenience problem that affects every aspect of maritime law. A ship owner who objects to a new regulation can simply re-register their vessel in a country that has not adopted it. The result is that a technology which has been proven for 100 years, which reduces fuel consumption by double-digit percentages, which pays for itself within a few years at current fuel prices, remains confined to a tiny fraction of the global fleet while regulators negotiate and ship owners calculate. The ships that do have rotors are almost all owner-operated, meaning the same company owns and charters the vessel. When the owner is also the charterer, the incentive problem disappears. The fuel savings go directly to the company that paid for the installation. These companies have confirmed the technology works, confirmed the economics make sense, and continue installing more rotors on more ships. The rest of the industry watches, calculates, and waits for someone to force their hand, a rotating cylinder. So simple that a single engineer built the first working version in the early 1920s using a physics principle from 1852. So effective that a ship used it to cross the Atlantic in 1926 on less than a third of the fuel a conventional vessel would have burned. So obviously useful that dozens of companies have now confirmed it works in real-world conditions on real commercial routes. First, it was a curiosity that a German engineer named Flettner turned into a working ship in the North Sea. Then it was a promising technology that the Great Depression made irrelevant before it could spread. Today, it is a proven solution sitting on fewer than 100 ships out of 50,000, waiting for the economics to align or the regulation to arrive. If this video changed the way you see the ships crossing the ocean carrying everything you own, subscribe. On this channel, the things that should have changed long ago always turn out to have a reason nobody explained. And the next video is going to show you exactly that.